This lesson is about solving root equations. We've spent a lot of time over the semester learning how to solve different kinds of equations. We found a method for solving linear equations. We looked at several methods of solving quadratic equations. We looked at solving higher order polynomial equations. And then we looked at solving rational equations. A root equation is an equation that has a radical in it. We're going to look at the square root first, and then we'll look at other roots, cube roots, etc. The only thing you can do with an equation is solve. And that means find the value or values of x that if I plug into the equation makes it a true statement. So we're going to have several steps here to solve root equations. The first step is going to be to isolate the root, the square root or the cube root or whatever. In this example, the part with the square root in it is all by itself on one side of the equation. My second step is going to be to square, if I have a square root, or cube, etc., if I have a cube root, both sides of the equation. And that eliminates the square root. So on this example, we put a parentheses around the whole thing and square it, and then we square everything on the other side, in this case just the 2. So the square and the square root eliminate each other, and we have x plus 5 equals 2 squared, which is 4. And then I can solve that linear equation, and I get x equals -1. So my third step is to solve the equation after you get rid of the radical. But we're going to see that when we have a square root or an even root of any kind, that we have to check our solution. And let me show you why. Let's say I had the statement 5 equals -5. We can tell that that's not a true statement. 5 does not equal -5. But if I were to square both sides, I would have 25 equals, and a negative times a negative is positive, 25, which is a true statement. So when I do this step of squaring both sides, I may be introducing an error into the problem. There's no other way to solve it. So what we do is we square the both sides, we get our solution, but then we have to check our solution. And remember that you're checking in the original equation with the square roots. So my check would be the square root of -1 plus 5 equals 2. That's what I'm checking. -1 plus 5 is 4. Square root of 4 is 2. So 2 equals 2, and it checks. So our solution is x equals -1. Let's look at another example. The square root of y plus 6 minus 1 equals 5. So on this, in my instructions again, would be solve. Find the value or values of y that make this a true statement. I want you to go ahead and see if you can solve this one yourself. And notice on this one, we do have to do our first step. We have to isolate the part with the square root by adding 1 to both sides. Then you can follow the rest of the steps. So pause the video, solve this, and then check back. All right, so we isolate the root by adding 1 to both sides. Then we square both sides. That eliminates the square root. Then we solve for y. And don't forget, we have to check in the original problem. And we see that we do get 5 equals 5. Sometimes students ask me a question at this point, and they say, remember back when we were solving quadratic equations and we took the square root of both sides, we had to take the positive and the negative version. Why do I assume that when I take the square root of 36, I get positive 6 only, and when I take the square root, say up here, of 4, I get positive 2 only? The difference here is that in the problems we're looking at now, the radical was already part of the problem. When you see the square root of some number as already part of the original problem, that implies the positive square root only. That symbol means positive square root only. When we solved for x here, we introduced x, or the square root, into the problem. We put it in there. And so we had to take the positive and the negative version. All right. Let's look at another example here. Let's say that I have, and I'm going to solve, the square root of 2x plus 7 minus 2 equals x. Our first step, isolate the radical. To do that, we add 2 to both sides. And we have x plus 2. Now, we have to be careful at this next step. When we square both sides, you cannot just square each term separately. Let me show you something here. Is this a true statement? 2 plus 3 equals 5. Yes, that is a true statement. But what if I squared each separate term? 4 plus 9 equals 25. 13 equals 25. That doesn't work algebraically to just square each separate term. That is not true. But what if I did this? This is a true statement. What if I put parentheses here and squared on both sides? Then I have to add the numbers first, and I get 25 equals 25, which is a true statement. So we need to be very careful here at this step when I'm squaring both sides. I'm going to square everything. So I have x plus 2 all squared. And remember, x plus 2 all squared is the same thing as x plus 2 times x plus 2. So I have to FOIL it out. The radical on the left is eliminated. I FOIL out the x plus 2. I'll end up with a quadratic equation with an x squared in it, and I'll use quadratic methods to solve. You go ahead and finish out this problem. Pause the video and finish out this problem. All right, so we squared the left. That eliminated the radical. We FOILed over here. And we have x squared plus 4x plus 4. Now we recognize this is a quadratic equation because of the x squared. So we get a 0 on one side, keeping the x squared term positive. So 4x minus 2x is positive 2x. 4 minus 7 is negative 3. Now I try to factor. And because there is no coefficient here, I know I have x times x, and then two numbers that multiply to give me negative 3 and add to give me 2. which are positive 3 and negative 1. So x is negative 3 or x is 1. Now I hope you remembered to check. You have to check each solution separately in the original equation. You cannot make any assumptions about the negative one will work or the positive one won't work, or if one works the other won't work. You have to check each one individually to see if it works. So let's check negative 3. Let's see, negative 6 plus 7 is 1 minus 2. So we have 1 minus 2, which is negative 1. And we see that this one does not check. So that tells me that the answer x equals negative 3 is not a solution. So I check the 1. And that one does check. So that tells me my solution is x equals 1. All right. What if instead of having a square root, we have a cube root? Cube root of 5x plus 4 plus 2 equals 7. Now on this one, we have a cube root, but we're going to start with the same process. We're going to isolate the root. By subtracting the 2. And now because we have a cube root, we are going to cube both sides. So the cube eliminates the cube root, and we have 5x plus 4, and 5 cubed is 5 times 5 times 5, which is 125, and then we can solve for x. And it turns out that with the cube root or any odd index on your root, you don't have to actually check, because you don't put any error into a problem if you cube. Because if you cube a negative number, it's still a negative number. So if you cube both sides and they weren't equal, they're still not equal. So you don't introduce that error you do if you have an even root. If you want to check all the problems just to make sure, that's totally fine, but it's not necessary to check with an odd root.